Okay, for this problem, you are first asked to find the area of R. You can see that the intersection points are 0 and 2 for X. And if you draw vertical lines, you can see that the top of each vertical line is following one of the two functions. The bottom is following the other one. And you are not allowed a calculator for this, so you have to figure out which one is which. And they both start with their y-intercept of 4. So if you think about the graph of cosine, hopefully you can see that the top of this graph looks like a cosine, whereas this other curve definitely does not look like a cosine. It looks like a parabola facing upward, which is what this problem is. So since the functions are named, you can use their names as you write the integral. That will find the area. So again, the top one was the cosine function, so that's g of x, minus the bottom function, f of x. And when you draw these vertical lines, that gives you a vertical length. That means the thing that pops it into area is multiplying it by a tiny horizontal cut. It is a dx, because the horizontal cuts are the differential part. Then x says this region exists from 0 to 2. You do not have a calculator, and it asks you to find the area, so you have to integrate. Integrating g, you need to do a u substitution. So I'm just going to put that over here and separately look at that. And look at solving this portion. So doing a u sub, u is what is inside of cosine, so basically pi over 4 times x. The derivative of u with respect to x is the constant pi over 4. When you multiply the dx over to the other side, and then multiply both sides by 4 over pi, you can see what dx will be replaced with. So this integral turns into 4 times cosine of what was chosen to be u, and dx is replaced with 4 over pi, which I'm going to write over here, times du, because I can pull the constant multiples all the way outside. And so this gives me 16 over pi, and then I integrate cosine, and I think carefully. I know I'm getting sine, but when I'm integrating, I ask myself, do I finish on a co? I finish not on a co, like cosine, cotangent, cosecant, so I do not bring in a negative. When I integrate and the answer is a co, I get negative. And if you think about the derivatives, when you take derivatives of trig functions, only the ones that are cosine, cosecant, and cotangent, those are the only ones that provide negative with their derivative. Then I can put the u back in. And I'm just going to write pi over 4 times x. And that is part of the problem. Let me write that down. Then minus, and I need to integrate f of x. F of x is a nice, pretty little polynomial. So when I integrate it, whoop, let's undo that. Okay. When I integrate it, I'm just going to use the power rule. So 2 times add 1 to the exponent, divide by the new exponent, minus 6 times, add 1 to the exponent, divide by the new exponent, plus 4 times x, and all of this is evaluated from 0 to 2. Any unit circle trig you are expected to do. So when I plug in the 2, I get 16 over pi times the sine of, if this is 2, then this is going to end up being reducing to pi over 2, and I'm going to have to find the sine of pi over 2, but I'm going to finish plugging the 2 in before I forget that I'm plugging the 2 in. So I get 2 times 2 cubed over 3, 4 divided by 2 is going to give me 2, so 6 times 2, ultimately 12, plus 8. And I still want to find this, but I'm going to first focus on just getting these numbers plugged in. If I plug 0 into x, I get sine of 0. How about we start off with just saying, we know the sine of 0 is 0, so I don't have to write as much. And then, oh, look, it's all 0. That means you don't have to actually write anything down with the minus 0. But I do need to find the sine of pi over 2. I can either think unit circle, and here's the angle pi over 2, and sine is a y-coordinate, so it is 1. Or I can remember the graph of sine and realize that when I'm at pi over 2, my sine value is 1. So 16 over pi times 1. And at this point, I recommend just don't do arithmetic. Leave it, call it a day. Don't feel the temptation that you need to that you need to bring together the negative 12 and 8. Someone's bound to accidentally write minus 20. You know, just don't arithmetic if you don't have to. Okay, so next thing up is write but do not evaluate. Oh, yay! I'm going to erase what I have in the previous problem to make some room. Okay, I love it when it says write but do not evaluate. An integral expression that gives the volume of the solid generated when r is rotated about the horizontal line y equals 4. Now we can see that this point is y equals 4. And other than that one point, the axis of rotation is above the region. When I make my 2 radii for the outer radius and inner radius that we'll subtract out, I start at my axis of rotation and I draw any line perpendicular from that axis of rotation through the region to the farthest of the 2 functions creating that region. I can draw it here, or I could have drawn it over here, either way. The inner radius from the axis of rotation, perpendicular from the axis of rotation, until it reaches the region but doesn't go in, which would be the closer of the 2 functions. And I can see what forms my outer radius and my inner radius. When I'm using rotational volume, I am creating pi r squared for the area formula. And it is pi outer radius squared minus pi times inner radius squared. Now, because these radii are vertical lengths, the other dimension not mentioned is horizontal. So to pop from an area formula into volume, I multiply by a teeny tiny horizontal distance. This is a dx integral. And that means I need to know where x is, where this region exists for x, which is 0 to 2 again. Then I'm ready to put in the specific functions. My axis of rotation is at y equals 4. To find a vertical length, I need to subtract the y top minus the y bottom. For the outer radius, the y top is 4. The y bottom is the parabola f of x. For the inner radius, that is going to subtract out the hole in the middle, shall we say. The top y value is 4. The bottom y value is g of x. And it said, write but do not evaluate. This is it. You are allowed to use the names of the functions, f and g, instead of writing out the entire expression of each function. All right, I'm going to erase this and move on to letter C. In letter C, the region R is a base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. So, you realize it's cross-sectional volume. For me, the first thing I look at is, who are we perpendicular to? Perpendicular to the x-axis. So perpendicular to the x-axis would be any vertical length. That means to pop this into another dimension, it's not going to be a tiny vertical cut because I already have long vertical distances. It's going to be tiny horizontal cuts, which will be dx. Now, with cross-sectional volume, it's always some area formula times the differential. The area formula is for a square. Length of side squared will give you the area of the square. The length of the side are these vertical distances, while x goes from 0 to 2. Ding, 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 ding. Every time you hit a particular x for this integral going from 0 to 2, it'll stop. It'll calculate the subtraction of these two functions as the radius, square it to get an area formula for a square, and make it volume by multiplying the tiny little dx. And then, so that's g minus f. And technically, because of this being squared, you are saved if you put the wrong subtraction order because you square it, it makes it positive. And it said, write but do not evaluate an integral expression that gives the volume of the solid. That's it, you're done. Yay!